You know that feeling when you're staring at a math problem and it just feels like a trap? Like it's designed to be tedious and make you waste a ton of time? Well, that's exactly what expanding a binomial can feel like. But what if I told you there's an amazing shortcut? Today, we're going to crack open the binomial theorem, a tool that turns all that grunt work into a really beautiful pattern.
I mean, just look at this thing. X plus y to the 7th power. To do this by hand, you'd have to multiply x plus y by itself 7 times. You'd multiply the first two, get a result, multiply that by another x plus y, and on and on and on. It's a total nightmare. And honestly, a recipe for making a tiny mistake somewhere that messes up the whole thing.
It's just pure algebraic chaos. But what if there was a hidden order to it all? A secret structure that lets you just write down the final answer directly with zero messy multiplication? Well, you're in luck, because there is. So here's our game plan. First, we're going to uncover that hidden pattern using a really cool visual tool called Pascal's triangle. Then we'll get to the real powerhouse, the binomial theorem formula itself. We'll run through some examples, I'll show you the common traps to avoid, and then we'll see why this thing is a huge deal, even outside of a math class. Okay, let's start with the most intuitive, kind of beautiful way to look at this problem. It's a pattern called Pascal's triangle. Think of it as our visual key for finding the special numbers, the coefficients, that show up in these big expansions. The beauty of this thing is how simple it is to build. You just start with the 1 at the top, then every number in the next row is just the sum of the two numbers right above it. So you see that 1 and 3 up there? They add up to make the 4 below them. That 3 and 3, they make the 6. It's that easy. And believe it or not, this simple triangle holds the secret coefficients we need. So how do we actually use it? Let's try to expand x plus y to the 4th power. Step 1. We just go to the row that starts with a 4, that's our n, and grab the numbers. We get 1, 4, 6, 4, 1. Step 2, we handle the variables. The x power starts high, at 4, and counts down to 0. The y power does the opposite. It starts at 0 and climbs up to 4. Step 3, you just put it all together, and boom, that's the full correct expansion. No long multiplication needed at all. Now, Pascal's triangle is awesome, but what if you need to expand something to the 20th power? You are not going to sit there and write out 20 rows of the triangle. For the big stuff, we need the formula that's actually generating the pattern. We need the real power tool, the binomial theorem. And here it is. I know, at first glance that looks pretty intense. You've got that big sigma for summation, you've got these weird parentheses, but trust me, we're just gonna break it down piece by piece. This is the engine that was building that beautiful triangle for us. Let's start with the heart of the formula, this little bit right here. We read that out loud as n choose k. This is the binomial coefficient. And it's not just some abstract thing, it actually represents a question. How many different ways can you choose k items from a group of n? This is the mathematical engine that generates every single number in Pascal's triangle. And how do we actually calculate n choose k without the triangle? With this formula, using factorials. This is what lets us jump straight to, say, the 20th row and find the exact coefficient we need without having to calculate all the rows before it. This is where the real power comes from. The last two parts of the formula are just our original terms, a and b. And notice the cool pattern in their exponents. As one goes down, the other goes up. And if you add them together, n minus k plus k, you always get n. It keeps this perfect balance all the way across the expansion. Okay, that's enough theory. The absolute best way to understand this is to get our hands dirty and actually put it to work. Let's solve a couple of classic problems you might see. All right, here's a classic test question. We don't need the whole massive expansion of 2x plus 3 to the 5th. We just want the single term that has x cubed in it. First, we identify our parts. A is 2x, b is 3, and n is 5. Now we want the term where our a part, the 2x, is cubed. Since the exponents have to add up to 5, that means our b term has to be squared. That tells us our k value is 2. So we plug everything into the formula for just that one term, calculate each piece, multiply it all together, and we get our answer. And there you have it, 720x cubed. The coefficient, the number we were looking for, is 720. See how cool that is? We didn't need to do the entire expansion. We surgically extracted the one single piece we needed. That's the efficiency of the theorem. So what about a binomial with a minus sign? This is a huge trip-up spot for so many students. The absolute key is to rewrite the problem. Instead of x minus 2, think of it as x plus negative 2.
Now we can just use our pattern for n equals 3 from Pascal's triangle. 1, 3, 3, 1. But you have to be super careful with the negative signs when you simplify. A negative number squared becomes positive, but a negative number cubed stays negative. Get the signs right, and the rest just falls into place.
Speaking of getting the details right, let's just call out the most common mistakes people make with this theorem. Because honestly, knowing where the traps are is the best way to avoid falling into them. This right here is without a doubt the number one error. When you have a term like 2x cubed, that little 3 applies to everything inside the parentheses. It applies to the x, but it also applies to the 2. It is not 2x cubed, it's 2 cubed times x cubed, which is 8x cubed. You've got to distribute that exponent to the number 2. The other huge trap is messing up the negative signs. We just saw this, but it's so important it deserves its own slide. Just remember the simple rule. An even exponent like 2 or 4 will make a negative number turn positive. An odd exponent like 3 or 5 will keep it negative. You have to track the sign for every single term, or one little mistake can throw off your whole answer. And one last kind of sneaky pitfall. Remember that in the formula, our counter case starts counting from 0, not 1. That means the first term is when k is equal 0, the second term is when k is equal 1, and so on. So if a question asks for the fourth term, you need to use k is equals 3. It's a classic off by 1 error, and it's super easy to make when you're in a hurry. So you might be thinking, okay, this is a neat math trick, but am I ever going to actually use this in the real world? Well, let's zoom out and see how this theorem is actually a massive building block in other fields. Yeah, so this isn't just some abstract algebra tool. Those coefficients, that n choose k we keep talking about, they are the absolute backbone of one of the most fundamental ideas in probability and statistics, something called the binomial distribution. And this formula right here shows the connection perfectly. This is used to calculate the probability of something happening exactly k times out of n tries. Like, what are the odds of getting exactly 7 heads if you flip a coin 10 times? And look, right there at the start of the formula, it's our old friend n choose k. The same math that expands polynomials also governs the laws of probability. It's all connected. In the end, what the binomial theorem really shows us is that something that looks incredibly messy and chaotic on the surface can be governed by a really simple, elegant, and predictable pattern underneath. And it kind of makes you wonder, right? What other things in the world that seem totally chaotic are just hiding a beautiful pattern waiting for us to discover the key?